Hi, welcome to Chapter 11 on optics. Optics is the study of light. In part 1 of this video lecture, we'll look at the basic properties of light. Chapter 11 is broken up into two parts. In this first part, we'll be looking at the basic properties of light, and in part 2, we'll look at an introduction to telescopes. Let's start out our lecture with a basic introductory video called What is Light?
Light is a strange thing. It isn't just what we can see. Light can be broken up into different types, and we call the whole family the electromagnetic spectrum. So even when it's dark, light is still all around us. Light can be created by making an electron oscillate. This creates an oscillating magnetic field and an oscillating electric field, which we call an electromagnetic wave or light. We often represent light as a wave. Just like water waves, light has a wavelength, a frequency, and a speed. The different colours of optical light have different wavelengths, and so does the rest of the electromagnetic spectrum. Gamma rays are the most energetic, whereas radio waves have the least energy. Even so, light is the fastest thing in the universe. In a vacuum, all light waves, even radio waves, travel at an incredible speed of 300 million metres per second. The Royal Observatory is overrun with squirrels. They're hard to miss during the day because they reflect visible light from the sun, but at night it's more difficult. However, they do emit infrared light, and if our eyes could detect it, we would be able to see them in the dark. If we pass high-energy X-rays through them, the squirrels look very different. Humankind has invented lots of different instruments to show us what our eyes can't see, like our Great Equatorial Telescope, which captures huge amounts of light and allows us to see objects that are tens of millions of trillions of kilometres away. We can see matter interact with light and change it. The gases in the Earth's atmosphere scatter blue wavelengths of sunlight, giving us blue skies during the day and red skies at sunrise and sunset. We can watch sunlight reflect off planets and the moon. During a lunar eclipse, red sunlight changes direction as it passes through the Earth's atmosphere and reaches the moon. And although visible light from stars can be absorbed by dust in space, we can detect the infrared light, which gets through to see baby stars hiding in nebulae. Light can even appear to stretch out. Since our universe is expanding and galaxies are moving away from each other, the light they emit is stretched to longer wavelengths. We call this redshift. Some galaxies are so far away that their light has shifted and stretched from visible to infrared, so we can no longer see them. Stranger still, the universe has unknown amounts of dark matter and bizarre black holes, so even if we can detect all the different types of light, there are still some things in the universe that will remain invisible to us.
So as we saw in the video, light is what's called an electromagnetic wave. And in particular, when we talk about light, we're usually talking about visible light. That is, light that we can see with our eyes. And so light in that sense is an electromagnetic wave that's visible to our eyes. Now, light travels at the fastest speed possible of anything in the universe. And this is a very special speed. It's called the speed of light. And the speed of light is designated with the letter c. And the value of c is 3 times 10 to the 8th meters per second. So that's 300 million meters per second. That also can be put into different units. For example, that's equal to 186,000 miles every second. Or in miles per hour, the speed of light is 670 million miles per hour. So, what is an electromagnetic wave? Well, that's a little bit beyond the scope of this course to really understand electromagnetic waves in any detail, but we can think of it as vibrating electric and magnetic fields that are traveling at the speed of light, c. So remember from our discussion of waves, we saw a wave can be represented as this curve shape here. This blue curve here represents an electric field that's changing with time. And along with that, there is a magnetic field sort of coupled to it that's in a different direction, as you can see. And this whole structure here, this electro and magnetic wave, is traveling at the speed of light. So this is, in a sense, what light really is. Now, where do electromagnetic waves come from? They come from accelerating electric charges, and usually this is coming from either vibrating electrons or atoms themselves. We'll look at the source and the origin of light in a little more detail when we study atoms in the next chapter, and we'll see how an atom can produce light. There's another very interesting and important way to think about light, and this was due to the work of Albert Einstein back in 1905. Albert Einstein proposed that light waves exist as tiny bundles of energy called photons. So Einstein's photon theory of light says that a photon is a particle of light, a tiny packet of electromagnetic energy that travels at the speed of light. And remember, the speed of light is given by c equals 3 times 10 to the 8th meters per second. So the whole idea and concept of a photon is very fascinating, because although we know quite a bit about photons and how they interact, we have lots of equations and theories that model the behavior of photons very precisely. At its root level, nobody really knows what a photon is. So it's helpful to model it as a tiny wave packet. And so if we think of a photon as this little group or cluster of waves, notice that this has a wavelength if we were to measure the distance between the peaks in here, and that wavelength would determine the color of light that's produced by these photons. So in this sense, a light wave or a light beam can be thought of as a stream of photons. So here we have a whole collection of photons all moving together, and all photons travel at the speed of light. So this is a very different sort of approach to light. Instead of thinking of it purely as a wave, we're now talking about light also as a stream of particles. Getting back to the speed of light, as I mentioned, is the fastest known or fastest allowed velocity for anything to travel. So the speed of light represents the cosmic speed limit. Einstein's theory of relativity tells us that nothing can travel faster than light. Now, why is that? Well, there are several very good arguments to show that it's impossible to exceed the speed of light. The simplest one just involves an energy explanation. It would actually require an infinite amount of energy to accelerate any object with mass to reach the speed of light. So no object that has mass can reach the speed of light. It's physically impossible. We can get small particles to approach the speed of light and get very close to the speed of light, but we can never actually get there, and we certainly can't exceed the speed of light. Now, light photons have no mass. They're a massless particle, and they must travel at the speed of light, but again, they never go faster. So here are some clever speed limit signs that you might see out in the universe, reminding everybody that the ultimate speed limit in our universe is c, the speed of light. So we've talked about two ways to model light. One is a wave and the other is a particle, and both are correct. It just depends how we look at light or how we do experiments with light, whether light behaves as a wave or does it behave as a particle. So light behaves like a wave when it's traveling through space, or for example, through the optics of a telescope or a lens. So in this sense, we can think of light as a wave here. It has a wavelength and a frequency and an amplitude and so forth. However, light behaves like a particle. Now these are photons, right? This is here showing a photon modeled as a little wave packet. So light behaves as photon particles when interacting with atoms, including the atoms in your eye or the atoms in a telescope camera or even in the digital camera in your smartphone. So in this sense, we think of light as a stream of photons. One of the most amazing things about light is that it represents just a tiny sliver in what is called the electromagnetic spectrum. And this is really an important and key part of the study of light. So when we talk about visible light, this is the light that we can see with our eyes. Our eyes are sensitive to light within a very narrow range of wavelengths or frequencies. So for example, at the smallest wavelength, our eyes can see about 400 nanometer wavelength of electromagnetic waves, and our eyes interpret this as the violet end of the spectrum. Notice as the wavelength changes here of light, this changes the color. So what our brain does, our brain interprets different wavelengths of light as different colors. And of course, this is an amazing sense to have with our sight, is that our brains can create the sensation of different colors, but it just depends on the wavelength. So notice sort of in the middle of the spectrum here, somewhere around 550 nanometers, we see that as a green light. And then as we keep going to longer wavelengths, we get into yellow, orange, and then finally somewhere around 700 to 800 nanometers, the deep red end of the spectrum just disappears to us. Our eyes can't see past this. However, if we look up here on the entire electromagnetic spectrum, we notice that this is the visible light right in here. These are the colors of the rainbow, which you might sometimes have heard Roy G. Biv. So it's red, orange, yellow, green, indigo, let's see, I lost blue, indigo, and violet. Sorry about that. But anyway, if we go past the red here, you can see we're now into the infrared. So infrared is something that we can sense and feel with our skin as heat, but our eyes don't see it. Now, that doesn't mean it's not there. It's just that our eyes aren't sensitive to infrared. And if we keep going longer wavelengths yet, we're now into the microwave part of the spectrum. This is where your cell phone actually works. It deals with microwave frequencies of electromagnetic radiation. And also, of course, your microwave oven works in this region of the spectrum here. If we keep going to longer and longer wavelengths still, we're now into the radio portion of the spectrum. FM, TV, shortwave, and AM radio is all in this very long wavelength part of the spectrum. Notice for visible light, the typical wavelengths are a few hundred nanometers. Remember, a nanometer is a billionth of a meter. So these are very short wavelengths. But notice when we get down to the radio part of the spectrum, the wavelengths can be hundreds or even thousands of meters long. What about if we go past the spectrum in the other end? Well, if we go beyond the violet, we're into the ultraviolet. And this is another part of the spectrum that our eyes are insensitive to. However, we know that ultraviolet rays are very dangerous to both our skin and our eyes. They can cause lots of damage. So even though we can't see them, they're still there, and these are high energy photons that can cause skin cancer and eye damage. Going beyond even the ultraviolet. Oh, I should mention here that we're pretty sure that bees, honeybees, are able to see into the ultraviolet part of the spectrum. So they can see colors out here past where our human eyes can see. So when they view the world, they see it as a very different place, I'm sure, because they see colors that we can't even imagine. Now, going past ultraviolet, we're into the X-ray part of the spectrum. And X-rays are extremely dangerous, except in low doses. Obviously, we use them in medicine. You've probably received dental X-rays and maybe even X-rays of your bones if you've ever had a broken bone. These electromagnetic rays are carried by very high energy photons, and these photons are able to penetrate through our bodies, and that's how we can see bones inside of a body using an X-ray camera. The highest energy rays here, which are the shortest of wavelengths, are called the gamma rays, and the gamma rays are produced by specific nuclear reactions, and also they are produced in the universe in deep space by things like colliding black holes and neutron stars. So this whole spectrum here represents the entire electromagnetic spectrum. And keep in mind again that we are only seeing a tiny little sliver of this spectrum somewhere in the middle. The rest of the universe is completely invisible to our eyes, but we will exploit these wavelengths later when we talk about telescopes, because telescopes can be designed to see in the gamma ray part of the spectrum, the X-ray part of the spectrum, ultraviolet, infrared, and even we have radio telescopes to look at the universe in radio waves. So we'll talk about that later in this chapter. So let's take a look at the relationship between the speed of light, the frequency of light, and the wavelength of light. So this is a review from earlier in the course. Remember from chapter 14 that for any wave, the speed of the wave, v, its velocity, is equal to lambda, the wavelength, times f, the frequency. So remember, if this is a wave, this could be any wave. It could be an ocean wave, it could be a wave on a string, or now we're talking about a light wave. The wavelength is characterized by the wavelength lambda, which is just the distance between the crests. And this whole wave, remember, is moving, in this case to the right, with some speed v. So when we're talking about light, we can replace v here with c, because remember that c is equal to the speed of light. So for light in a vacuum or in air, where it actually travels at this speed, this equation up here becomes this: c equals lambda times f. Now, lambda here is the wavelength which we measure in meters, but quite often, especially when we're talking about light, the wavelength will be given in nanometers. So remember that 1 nanometer is 10 to the minus 9 meters. That's 1 billionth of a meter. And then f is the frequency of light, and that's in cycles per second, or hertz. So let's look at a little example here. Determine the frequency of green light, which has a wavelength of 550 nanometers. So to figure out the frequency f, we're going to solve this equation for f. So we're going to divide both sides by lambda. So f is equal to c over lambda. Well, c is the speed of light, which is 3 times 10 to the 8th meters per second. Lambda was given 550 nanometers. Remember, we have to convert that to meters. So it's 550 times 10 to the minus 9 meters, because each nanometer, again, is 10 to the minus 9 meters. So on your calculator, you can do this, division problem here and do this calculation, and we get our answer. Our frequency of green light is 5.45 times 10 to the 14 hertz. Now this is obviously a very large number. This is 545 trillion hertz. So one of the messages here is that light has very high frequency. Its wavelength is so short and it's moving so fast that the frequency is very high, and obviously we're not going to be able to detect this frequency when something is vibrating 500 trillion times per second. What we're going to do in the rest of this part of the lecture, part 1 here, is just sort of go through a survey of basic properties of light. And so we're not going to go into any great detail here, but this will give us a good description of, about the properties and characteristics of light. So the first ones that we're going to talk about here are absorption and transmission. So absorption just means that light is absorbed by the atoms in some materials and converted to heat. So if you try to shine light through wood, for example, the wall of your house, obviously the light doesn't get through. What happens is the photons are absorbed by the atoms and molecules inside the wood, and that energy is ultimately just converted to heat. So we say that wood is opaque. By the way, this also explains why things get hot when they're set out in the sun. Okay, that energy from the photons in the sunlight is absorbed in that material, and that material heats up over time. Sort of opposite of absorption is transmission. Transmission is when light passes through a material. So materials like glass or plastic or even water are transparent. The light can go right through without getting absorbed at all. And all of the photons then basically are emitted from the other side of the object, giving it transparency. One of the basic properties of any wave is that waves will reflect off of surfaces. So reflection is what's actually happening is the light rays are absorbed and re-emitted, and this is basically what reflection is, by an object. So here's our observer here, his eye, and we're looking at a tree in the daytime. So how do we actually see that tree? Well, what's happening is light is coming from the sun and it's reflecting off of the tree. And you know, some colors are absorbed, others are reflected, and in this case the green light is reflected off of the tree, and we see the green leaves of the tree. Reflection obeys a very simple law called the law of reflection, and the law of reflection says that the angle of incidence is equal to the angle of reflection. So what do we mean by that? Well, let's say we have a mirror here laying flat on the floor. Let's imagine this perpendicular line coming straight up off of the mirror. So if we were to take a flashlight or a laser pointer, say, and point it down here, this angle right here is called the angle of incidence. All right, this is the angle with respect to this perpendicular line right here. So let's say in this example here, this angle is 25 degrees. Well, what that means then, the law of reflection tells us that this reflected ray, which bounces off the mirror, also has an angle of 25 degrees. This is the angle of reflection on this side. The law of reflection can help us explain how mirrors work. So when we look at an object in a mirror, so here's a little dog sitting here, and this is a mirror on the wall, let's say, and we're over here and we're looking at the reflection of this dog. Well, what actually happens is, remember that this light ray coming from the dog bounces off of the mirror according to the law of reflection with the same angle that it came in and strikes our eye here. Now, the way our brain works is our brain and our eye sees this beam of light, or this ray of light, coming from not here, but we see it as if it were extended in the same direction behind the mirror. So the image of an object in a mirror is behind the mirror the same distance that the object is in front of the mirror. And you can very quickly test this. Next time you look in a mirror, for example, in your bathroom, notice where your image is in the mirror. You're not seeing yourself right at the mirror. You're actually seeing yourself behind the mirror, the same distance that you are in front of the mirror. One of the other fundamental properties of light is refraction. Refraction means that light changes speed and bends when passing from one material to another. So you can see in this picture here, this is a cube of probably glass, I'm imagining, and here's a light beam that is shined onto this glass. So notice the beam comes in here at this angle here, but it doesn't go through the glass in a straight line. It actually bends when it comes into the glass, and then it bends again when it leaves the glass. So this is called refraction, the bending of light as it passes into different materials. And this can be understood from the fact that the light actually slows down inside the glass, which requires it to change directions. Now, in order to see this, imagine you have a marching band, or maybe a group of soldiers, all lined up in rows and columns. This is looking from the top, obviously, and they're marching across the grass in this direction of the blue arrow. All of a sudden, they encounter a deep, muddy field here. All right, where the mud is, up to their knees. So what happens? Well, as they start entering the mud, they start slowing down. So they start to bunch up closer and closer together. But these soldiers or marchers over here are still marching fast because they have not reached the mud here, which is this region down here. So what happens is these rows of soldiers, all right, which represent wave fronts of light, they change directions as they go into the mud because they've slowed down. So notice the rows now are going at a slightly different angle. They've changed directions. And this is actually a nice analogy. This model explains why light, first of all, why it slows down when it gets inside the glass, and also it explains why the path of the light bends or refracts. One of the most important, the most important application of refraction is the idea of lenses. So what a lens is, it's a curved piece of glass, and the two basic types of lenses are a converging lens and a diverging lens. And this is what's called a ray diagram. So this is looking at the converging lens from the side. You can see it's wider or thicker in the center, and it tapers down at the edges of the lens, and this is also called a convex lens. So what happens here are incoming light rays. Remember, when they hit the glass, they change direction, they refract. And because the curvature is more up here than it is in the center, these rays out here are going to bend more than the ones in the center. Actually, the center ray doesn't bend at all because it's going straight into the glass. But this lens is ground or shaped just right so that all of these rays converge to a single point called the focus point or focal point of the lens. And this is where an image is actually formed. And we'll be using this to show how a telescope works later. This is a refracting telescope which uses a lens to refract the light rays. Inside of our eyes, the lens of your eye is a converging lens just like this, and it forms a focused image right back on your retina where the optic nerves are connected. The other type of lens is a diverging lens, and it's curved the opposite direction, as you can see. So incoming parallel light rays here actually diverge instead of converge. They spread apart. And this type of lens is used for different purposes, one of them to correct vision defects in eyes. Another property of light is called dispersion. And dispersion was discovered by Isaac Newton, who, in addition to his work in the laws of motion that we studied earlier, and also, of course, his universal law of gravitation, Newton also was fascinated by light and came up with several laws of optics as well. So dispersion is the separation of white light into colors. And the idea here is that different wavelengths or colors of light refract or bend at different angles. So this is a prism. This is looking at a glass prism from the side, and here is a beam of white light. For example, this could be a ray of sunlight that's let into this prism. You can see what happens as it comes into the prism. The light starts to disperse into its colors of the spectrum, and then as it leaves the prism here, it disperses even more. So what comes out of this prism here is not white light, but we see all of the colors that make up white light. So Newton discovered that white light, for example sunlight, is actually the result of all the colors of the spectrum being mixed together. And here again we see the visible colors of the electromagnetic spectrum, Roy G. Biv, the red, orange, yellow, green, blue, indigo, and violet. And by the way, it was later discovered that this over here, if we were to place a thermometer, even though it's not in the visible part of the spectrum, the infrared rays are hitting here, and they noticed that the thermometer actually warmed up even though there was no visible light there. And this was one of the ways that infrared radiation was discovered. Later on, when they developed ultraviolet detectors, they found that if we placed the ultraviolet detector down here, it would detect some ultraviolet rays, which again we can't see, but are beyond the violet part of the spectrum. Why is the sky blue and why are sunsets red? Well, this is one of the properties of light as well, and this is mainly due to something called scattering, which is where light rays basically scatter off of particles in the air, including the air itself, the air molecules itself. So during the day when we're looking up, the sun is directly overhead, what happens is the light from the sun is scattering off of the atmosphere of our Earth, and blue light scatters more than other colors. We saw this actually in the last slide with the prism. Remember that the blue light was the one that was bending or refracting more, and the same kind of process happens here with scattering. So the sky appears blue because of that scattering angle. Now later in the day, when the observer here is looking horizontally towards the sunset, remember all the blue light is scattering out in different directions. The only light that gets through is the red end of the spectrum because it scatters the least. So at the end of the day, and also during sunrises, of course, at the beginning of the day, it's the red light that is able to penetrate through the thick part of the atmosphere here when we're looking in this direction, giving the sunset the beautiful orange and red colors. Another property of all waves, including light, is called diffraction. Diffraction is when waves spread out when traveling through small openings. So this is looking down from above at some sort of barrier here with an opening. You can think of this like a wall, and here's a window or a door. So if these are sound waves coming towards this opening here, obviously the sound doesn't just come straight out, it spreads out, and we can hear the sound if it's loud music from a neighbor's house or whatever. We'll hear that from different locations. So this is called diffraction, and light waves diffract as well. This is a demonstration that I normally show in class, but I can illustrate it here very, very easily. If you take a plate here, like a metal plate that has a thin little narrow vertical slit in it like this, okay? And if we shine a bright laser beam on this, and we usually, we do this in the dark, we turn off all the lights, and we shine this laser beam through here, what happens is the laser beam spreads out in the horizontal direction, not in the vertical direction, which you might expect because this slit is vertical, but it actually spreads out only horizontally in this direction. And what we're seeing here is this property up here called diffraction. So this pattern shown back here, this is an actual photograph of what a laser looks like when it's shined through a vertical slit. We end up with a horizontal spreading of the laser light. And notice there are little light and dark spots. This is called interference, which we're going to talk about next. We talked about interference when we were discussing sound waves earlier in this course. And interference is really a fascinating property because remember that interference can produce either constructive interference when the wave is made stronger, or destructive interference when the wave is made weaker or even disappears because it's basically the peaks and crests of the two waves are canceling each other. So for light, we can see this very easily. So look at, this is another diagram showing a top view. So here, imagine again like a wall. All right, we're looking down at the wall from above, and the wall has two openings or two windows, one down here and one up here. And so these lines here represent light rays coming in from left to right and shining through these two openings. All right, so these are called wave fronts. These lines represent crests, and in between the crests are troughs. So remember that when light goes through an opening, it diffracts, meaning it spreads out. So that's why these lines are now curved. Well, remember when the crests overlap, for example, where we see two lines crisscrossing here, that represents constructive interference. And if that shines on a screen or a wall over here, that will produce a bright band. In between those bright bands are destructive interference, which you can see as the regions in between the dark lines here. And that's where the light actually cancels each other out. And so what we're going to see are dark bands in between the bright bands. So there's a couple of experiments that we typically do in class. One is to shine a laser beam. In this case, it's a bright green laser beam. And notice again, here's our plate or our wall, right? And notice there are two closely placed slits right next to each other. And as the beam goes through these slits, it spreads out from each slit and interferes with itself and produces this pattern. So this is an actual photograph of the laser beam pattern on the wall or on the screen behind, and notice there are bright regions, constructive interference, separated by dark lines, which are destructive interference. Now, you don't need any fancy equipment to show this effect. In fact, you can do this at home right now. You can take two fingers, either from your same hand, or I like to use my two index fingers, one from each hand, and place them very close to each other and put it right up to your eye and look at a bright source of light, such as a lamp, or maybe a window if it's in the daytime. And if you hold your fingers just at the right distance apart, you will notice a bunch of dark and white lines. They look like little hairs almost going vertically between your fingers. What you're actually seeing there are these constructive and destructive interference patterns due to the diffraction and interference of light as it comes through the space between your fingers. So, this is an experiment you should try at home, and it's kind of interesting to see that, you can experience the diffraction and interference of light without any special equipment at all. So go ahead and give it a try. Our last topic here on the properties of light is another fascinating one. It's called polarization. Polarization is the property of transverse waves, such as light, such that they oscillate or vibrate in the same direction. And there's a nice analogy to this thinking about wiggling a rope with a picket fence. So if the pickets are vertically, as shown here, the rope can wiggle up and down, but it can't wiggle back and forth because the waves basically hit the fence and are blocked by it. So by using something called polarization sheets, we can very easily and graphically demonstrate the properties and effects of polarized light. For example, we can place one film vertically to create the light polarized in this direction, and then by rotating the second plate in the other direction, we can completely block the light out. So let's go ahead and watch a video that another instructor has made to demonstrate the effects of polarization, and then we will reconvene in part 2 of this video later.
Now, you might be wondering, is light a transverse or a longitudinal wave? How could we test this? This device is called a polarizer. It's designed to let waves get through in only one direction. As I send the wave out, it gets through fine that way, but this way, I can't get the wave through. No matter what crazy wave I send, only the left and right components get through. It's been polarized. Now that only works on transverse waves. If it works on light, then light is a transverse wave. Because light can be polarized, we know it's a transverse wave. This is a polarizer. It's polarizing up and down. This is another polarizer. It's polarizing left and right. When these two are crossed, we get absolute darkness, zero transmittance. But if we cross them the other way, light still gets through. They're polarizing together the same way. Unpolarized light, for example, from the sun, travels to a polarizer, which polarizes it up and down. The light continues and hits another polarizer, but this polarizer is side to side. That cancels all the light. No light gets through.